Saving energy is a major global socio-economic target in energy efficiency as well as environmental point of view. Hello, good morning all. This is Sapna from MES Panani College, Kerala, here to present a poster on tailoring of optical bandgap and microstructure profiling of vanadium-based complex compound systems. Vanadium pentoxide have recently been acquired a great deal of attention in diverse device applications due to its outstanding properties. The non-stoichiometry associated with vanadium pentoxide can be used to modify its properties, and suitable ions may be incorporated in the crystal structure without affecting the crystal matrix drastically. Here, we synthesized of VBIO and VMNO complex compounds by solid-state reaction technique in the temperature range 570 to 640 degrees Celsius and carried out different characterizations such as XRD, UV visible spectra, photoluminescence. And this is the XRD pattern of the prepared samples for different mode concentration. And this is for VBIO system and this is for VMNO system. And XRD peaks analogous to pure V2O5 along in different planes, and it shows a dominant peak at 2 theta equal to 20.54 degree along 001 direction. And the patterns are high in intensity and sharp, which has improved the crystalline quality of the samples. And all the samples show same phase and structure as that of pure V2O5, which can be indexed with orthorhombic structure in PMMN space group. And this is the estimated grain size and lattice parameters. The obtained data shows insignificant variation in lattice parameters, suggesting the successful insertion of bismuth and manganese ions. And this is the diffuse reflectance spectra of as prepared samples. This is for bismuth and this is for manganese. It shows a sharp absorption edge from 500 to 650 nanometer, and there is a slight variation in reflectance edge, maybe due to the bandgap restructuring, which alters the conducting behavior of the samples. And this is the estimated bandgap energy using Kudelka-Monk function. And from this, it is clear that as the mole concentration increases, the bandgap energy of VBIO system increases, and which can be explained using Morse-Bernstein effect. While in VMNO system, as X increases, the bandgap energy decreases, since as free carrier concentration increases, the bandgap widening is counteracted by a narrowing caused by the correlated motion of charged carriers. And this represents the TL spectra of the prepared samples at room temperature. Major emissions were observed around 370, 400, 460, and 535 nanometer. And the emissions have been mostly attributed to the radiation transition between electron-hole combination. The emission at 370 nanometer is due to valence uncertainties of vanadium, and at 400 nanometer indicates the excess presence of V4 plus ions along with V5 plus ions in crystal. And 460 nanometer emission has an energy higher than bandgap energy and might be due to the recombination of electrons from higher levels of valence band and conduction band. The low intensity indicate oxygen deficiency related defects in crystal. All these emissions are relatively strong and broad, and this is an extremely desirable feature required for different sensor applications. And so we synthesized VBIO and VMNO complex compound using solid-state reaction technique. All samples have orthorhombic structure with prominent orientation along 001 direction and matches with pure V2O5. And the bandgap energy calculated matches well with the reported bandgap of metal oxide substituted V2O5, and PL spectra bandgap is found to be restructured due to the presence of bismuth and manganese ions. Thank you all for your kind attention.